So I will talk about, it's kind of like a reality check, right? I mean, if we are talking about the big orbits somewhere in the very big space, well, let's check if we can do something for small orbits where we can, for example, classify them and everything. So, so I'll be talking about G will be, say, reductive group or semi-simple, maybe later. And V is, say, irreducible representation. And, well, and actually I'll be working under the assumption that there are only finitely many G orbits. I'll tell you a little bit about the list because these are classified. I'll tell you a little bit about the list a little later. But now if you are in such easy situation, let me maybe talk about what algebraists would like to do in such situation. What is the algebraist dream wish list? What could we do with the orbit? So, so the wish list. Well, you have this. So let's take S to be the coordinate ring C of V. I'm working over K equals C. So you might want, of course, you have orbits OX. Then I have this, actually it's better to talk about orbit closures because they are somehow, well, they are closed algebraic sets. So what would I want from this to know about this ring? So first of all, as it was already observed several times, it's very important to know whether COX is, or the coordinate ring of the orbit closure, whether it's normal. And the point is then, in such situation, the coordinate ring of the orbit itself is equal to the coordinate ring of the orbit closure. Then, what you would like maybe to do, you would like to know, so S mod I will be my coordinate ring of this orbit closure OX. Maybe you...
Boundary small.
Excuse me? Which boundary of the orbit closure? No, I just look at all orbits in representation with finitely many orbits. But it will be just concrete examples. You have lists, so sometimes the boundary is not small. Okay, so there will be non-normal orbits in what I'll be talking about.
If it's not normal, you can still have poles on the boundary. So shouldn't it be like COX poly or something?
All right, well, so maybe if it's normal with one additional assumption, clearly that's the reason why we are interested in normality, right? That you can deduce that.
You can deduce, but you do not have equality.
No, yeah.
Well, the restriction map? Oh, I see, okay. Yeah, if the boundary is plus codimension 2, yeah, okay. Then it implies. But anyway, that's the reason to study normality. That's the only point I want to make. Then you would maybe like to calculate the Hilbert series of this S mod I, which is summation. It's a power series. You just want to calculate. This will be graded rings. All those orbits will be conical varieties. So, so this is a Hilbert series, and it always will be of the form n is dimensional V, I guess.
So do you know that the singularities are rational, for example?
That's what I'm getting at. That's right. You would like to know also. That's right. So that's a wish list. And then I'll tell you what is true in those cases and what's not true, and in what cases we cannot decide it. You would like to know whether they have rational singularities, but maybe let me talk first of all about Cohen-Macaulay property. And in particular, this is related to syzygists. So when you have this S mod I, your coordinate ring of the orbit closure, it will be a graded module over this. This is a just polynomial ring.
What is n?
N is dimension of V. So this is just Cx1xn. So then it's a graded module. It will have what's called this minimal free resolution. So basically, well, there'll be a sequence of free modules and actually finite by Hilbert's syzygy theorem. So Fi is a free module, S module. So really S to some power beta I. And these are just, so you can think if you choose the basis in those free modules, you can choose, you can think of this, you have D1, this D1, D2, up to ds. So these are really some matrices. And well, so you see the point is you will always have one generator because it's just a factor of the ring S by some ideal. So for example, F1 will tell you about the equations. Okay. The module F1 will tell you exactly what are the defining equations. So that's another thing. Maybe I'll talk about. Let me talk about defining equations. You want not only set theoretical equations, but also defining equations, and this will be the first step in the resolution. I still didn't define for you Cohen-Macaulay. So a typical example, just to give you a very small example of this pre-resolution, just to see what it is. Let's take the 2x3 matrix. So your representation actually will be some home from 1c squared to c cubed. And let's take I to be the ideal generated by 3 2x2 minors of that matrix. Then already Hilbert knew that this resolution will be like this. You have S mod I. Well, it's a cyclic S module, so there's just, generated goes to 1. It's just an S module generated by 1. And here, of course, you will have S cubed because you have 3 generators. Delta 1, 2, maybe let's write minus delta 1, 3, delta 2, 3. And then if you think about it, you will find some linear relations. Namely, if you write the transpose of this matrix, you will see by Laplace expansions of the matrix with repeated row that the composition is 0, and it's not difficult to prove that this is everything, right? So this is an example of the minimal resolution, which is slightly non-trivial because that's not something that you would guess, like in 1 minute. Maybe it would take, I don't know, 2 hours, no? Or something like that. You were talking about 2 hours. Well, anyway. So that's what we are talking about here. So it's always graded, so I would sometimes write this. So that's, the goal will be, the kind of ultimate goal will be, can we find those even resolutions of the orbit closures? All right? So that's kind of what... Cohen-Macaulay I did not define. Cohen-Macaulay has to do with length of this resolution. So OX is Cohen-Macaulay. If and only if the length of this resolution is just a codimension of the 0 set of I. And that's also very useful when you deal, the reason really, one of the reasons is it's useful because you see sometimes if you have the candidates for the equations of the variety, if you know that it's Cohen-Macaulay, it allows you to actually conclude that you really got all the defining equations. Okay, so that's useful for equations. Let me just write. Defining equations, for example. Yes, and then there are these, kind of stronger notions, so-called rational singularities. I will not...
So if you have the candidate equations, what do you take? You take the resolution of the candidate equations and then you see if it has the same correct length?
Well, there are methods sometimes to prove that something is Cohen-Macaulay without defining equations. So if you know for some other reasons that S is Cohen-Macaulay, then if you know that your equations are good on the open set, then you will know that they are good everywhere. That's kind of, generically reduced versus reduced. So that's really somehow immediate profit you can have from the Cohen-Macaulay. And then rational singularity is a stronger property, but let me not go there. It's kind of cohomological formulation. So that's your wish list, all right? So
the minimal resolution.
For the minimal resolution, that's right. For the minimal resolution, so I assume a resolution is minimal, so, I will not have like ones in those matrices. I could have stupid generator 1 minus 1, right, or something like that. So you allow only, in this graded situation, all entries of matrices will be polynomials of homogeneous polynomials of positive degree. So that's your wish list. All right, so let me now talk a little bit about which representations we get, which irreducible representations of reductive groups which have finitely many orbits. Maybe I have to assume that the group is semi-simple and connected.
Sorry,
Yes.
Did you say any of the benefits of rational singularities?
No, I didn't. That's right. That's a good comment. For example, it implies that it's Cohen-Macaulay.
Also, you could say that the Hilbert series is actually a polynomial.
That's right. You can also say that Hilbert series, and actually, yeah, in some cases you can even claim that it's a polynomial, even. Okay, if everything is generated in degree 1, I mean, you can. That's right. Hilbert series, which usually, if you take dimension of this SAD of the D's homogeneous component, it will become polynomial only for big D. But if something is rational singularities, there will be no holes. It will be polynomial right away. So that's very useful, and because you know the degree of that polynomial. All right, so what's the list I'm interested in? List of VG, GV with finitely many orbits. And the list is interesting by itself because it's also related to maybe something about we'll be talking about tomorrow, quiver. So I'll give you a list of some representations, groups and representations, and the claim will be that they are basically like almost all representations with finitely many orbits. So this was done by Katz and Winberg, classified Katz, Winberg, and I guess 1980s, right? More or less a long time ago already. So here's it is. Well, first of all, let me just recall about Dynkin diagrams. So we know that simple Lie algebras are classified by root systems, also by Dynkin diagrams. So there are, A, N, B, N, there are 4 series, C, N, D, N, E6, 7, 8, F4, and G2. So maybe, we have A, N, but maybe, I don't want to write the list, everybody can look it up if you don't know it. Anyway, so the corresponding Lie algebras here would be the classical ones, SLN, SON odd, SPN, SON even, for example, and then for those, well, they are quite exotic. So our representations will be parameterized by a Dynkin diagram with a black dot. Okay, so black dot, and then I'll tell you how to associate. So data, Dynkin diagram with a black dot.
But your group.
I mean something like this.
Some people call these marks, I think.
Well, okay, this is black, this is white. Okay, so on whiteboard it's okay, right? On blackboard it works the opposite way, but here it's okay. So that's so I basically, okay, I really distinguish a simple root. Okay, so this corresponds to, I have my Lie algebra corresponding to the big root system. This corresponds to certain Z grading. I will not elaborate on that. It's finite dimensional, so it goes like this. But let me just give you an example of the Z grading, exactly the example corresponding to this. Okay, and then you will get the idea. So clearly, the big algebra here, I have 6 dots, so it's SL7. All right, but if I would forget the black dot, I get the disjoint union. So this would be SL3, and this would be SL4. All right. So you see what you do, you write your GL SL7 in just block form, 3 times 3, 3, 4, 4. And here you get, well, kind of SL3 and SL4, but actually you get one more dimensional space because there's like something in diagonal matrices. But here you get something, you know, that I call G1, and here I call G minus 1. This would be G0 plus C. So you see, you'd get basically clearly the commutator will respect the grading. So I get that G equals G minus 1 plus G0, which will be actual SL3 cross SL4 cross C, plus G1. And this G1 will be really home from C4. Well, I reverse the blocks probably, I don't know. C4 to C3. So maybe it's C4 star tensor C3. Anyway, so you get those gradings that are more complicated for more complicated algebras. It doesn't matter. And our representation we are interested in, okay, I didn't tell you I have this datum. My representation V will be always G1, the first graded component. So in this case, will be just home from C4 to C3. So 4 times 3 matrices, all right? And of course, the group then, well, or the Lie algebra, but then the group will act by rows and column operation. So this is a very simple example, the simplest. I should tell you what the group is. So the group G will be, well, the group G0, which corresponds to the smaller root system, which, okay, one has to take adjoint group because you have to hear choices as to which group do you take. And then there's one copy of C star which corresponds to this kind of diagonal element that we left out, okay? So that's the group, and then Weinberg theorem is that, Weinberg theorem, here.
So you're taking Levy and the unipotent, nilpotent, and the lower.
That's right, exactly. Mm-hmm.
But in general, you would have more than G1. You will have more.
No, you can just take G1. G1.
He only wants G1.
G1.
You only want G1, but there, in general, there are other G2 and so on also.
Yes. Oh, yeah. In general, it can go, that's right. But your representation is G1. You take the group G acting on G1. And the theorem is that GV has finitely many orbits. And actually, Katz then classified representations with finitely many orbits. There are only very few irreducible other representations with finitely many orbits. Okay?
Katz-Dadok?
That's right. Katz and then Katz-Dadok, there was a correction. That's exactly, yeah. So Katz-Dadok. Katz-Dadok. These are almost all. And almost means there are really very few exceptions. So one can just make a very small list.
Oh, you can enumerate them?
Yeah. It's just like probably one series and one example, I think, or something like that. Yeah. So it's just really accidental that there are some others that have finitely many orbits. Okay. So that's quite nice.
So any black dot will do. Is that the statement?
Any black dot will do. That's right. And let me just show you also how.
For this. Yes.
That's right.
Only G1, there's only a few.
Can you give just one quick example?
Yes, I will give you several concrete examples. So, because of course now, if you take some complicated Lie algebra, that you don't know what it is, like algebra of type E6, right? How do you figure out G1? But it's very easy to figure out G1.
Yes, can I ask one more question?
Sure.
So basically it says that all these things come from tame quivers, is it, in some sense?
Well, I mean, they don't come from quivers. It's kind of an analog on just representative, for irreducible representation of algebraic groups of kind of this trichotomy, which is not true like on the nose, but something quite similar is true. Because you can always, these are so-called Weinberg representation of type 1, if you take extended Dynkin quiver and take a black dot, you can also define G1, and this will behave very nicely. Like the ring of invariance would be a polynomial. It will behave like an adjoint representation for the group G. Okay, so there's again kind of trichotomy, but it doesn't work on the nose because there are other representations, irreducible representations, for which ring of invariance is a polynomial ring. And here the list is quite extensive. This was obtained by Littleman. So, but at least for this Dynkin quiver is a black dot and extended Dynkin is a black dot, they exhibit very similar behavior to finite type and tame quivers, okay? Yeah, so let me give you examples because G1 is very easy to figure out, okay? It's like, it seems, what do you do with E6? But the point is like this. Let's think about just AN diagram for a moment. So if you think about representation theory, then I have SL5, say here. Then sometimes, you know, the most important are so-called fundamental representations, okay? Fundamental representations of SLN. So, you know, this is SL of some E, which is E is Cn. Actually, in our example, is C5. So sometimes you think about this Dynkin diagram as, you know, each node will correspond to one of those fundamental representations. There's natural labeling. So you see for SL5, you would have here wedge 1, these are exterior powers. So you have wedge 2E, wedge 3E, wedge 4E. All right? So that's how you think about those fundamental representations. So it turns out that if you, it's very easy to figure out G1. And let me give you some examples. So, you see, suppose I have the example like that. All right, then basically you think of this as being diagram corresponding to a representation. So here you got SL7, okay? And here, you see, the black dot touches the third one. So this is wedge 3C7, and the group is GL7 because you have to pull back the torus. Okay? Now, if you have the situation like this, let's take the middle dot, black dot, for example. Then, well, it touches three things. The smaller root system is, you know, SL3 cross SL3 cross SL2, right? Well, cross C if you take Lie algebra. But now what's the representation? It touches, here it touches the second, so it will be C3 star, tensor C3, tensor C2. Okay, and as a group you would have to take product of SS3 and one copy of C star. All right, so you can see actually from this, you know, you can see this nice exercise. Well, everybody knows, for example, that if you have wedge 2E, right, that it always has finitely many orbits. Q-symmetric matrices up to row operations, well, you have only rank. Well, this is just, you see, the N diagram. Okay? But if you look at the wedge 3E, where E is Cn, and you ask, when does it have finitely many orbits? It turns out that you can go only up to E8. And then for E9, you know, if the dimension is 9, it does not. And it actually, that's what the theorem says, actually. It's so has finitely many orbits. Finitely many orbits. For
SON, right? The group is SON.
No, you add this torus, so actually it will be GLN. Because remember, you always have to put back one copy of C star. So if to SLN you put back copy of C star, you can take GLN. Okay?
So here it's GLN option and wedge 3E.
That's right. Or wedge 3CN. So it has finitely many orbits only for n smaller or equals than 8. One has to be careful with triple tensor products because if you take C2 times C3 times Cn, which does not give, these are exactly the exceptions, okay? So these are the bigger things, but because basically, well, anyway, it doesn't matter, but this one series of exceptions. So you see, so now if you have your representation, you can actually test whether you have a chance or not. You just draw this diagram.
We have an example of Lie group with finitely many orbits, which is other than GLN.
Oh, sure, yeah, of course. You know, you have, for example, if you take E8, that's right. You have, you know, like
Even Easter.
this, and you get diagram of type Dn, so it will be one of the half spinor representations. Okay, yeah, because you can put black dot anywhere you want. All right? All right. So these are our representations. So let me just tell you briefly what is known and what methods are used. I will not go into the details, but so this is Well, there are many people working on this. So as I said, Katz-Winberg. So first of all, classification of orbits. Also done by Winberg. And he kind of gave two statements, okay? One, he just said that basically you have this G equals summation GI, the easy description, but not easy to work with practice. You just take a nilpotent orbit in G, intersect with G1, and take irreducible components. Right? So this is, you get all the orbits. Just coming back to our example, let me just do the example. G1, G minus 1, and G0, our SL7. Now you see clearly if you take the matrix of the type 0, 0, 0, X, well, you get the matrix that actually certainly X squared is 0. So basically, well, I mean, you get only, sorry, that's right. So first, I mean, what are the orbits in Hom C4, C3? The orbits, we allow row and column operations, so these are just rank varieties. Matrix of a given rank give you a variety. But now suppose now I take a nilpotent orbit, which are nilpotent, they're given by partitions of 7, right? And you look which of them is in G1, then you get a nilpotent matrix of this type in SL7, so this will be only orbits with X squared equals 0. So then a simple combinatorics shows, well, you can have some Jordan blocks of size 2, and this will give you the rank. So that's how it works. You see that nilpotent orbit intersected with this G1 will give you a matrix of a given rank.
And this way you get all the...
And this will give you, that's right. If you take, but you have to take components. And sometimes nilpotent orbit intersect very badly. There are several orbits of different dimension and so on. Everything else can go wrong. But this. And then...
what do you mean by X squared?
Well, as a 7 by 7 matrix.
7 by 7 matrix.
Yeah, that's right. Because now you are looking at nilpotent orbit in SL7. Well, it's a matrix such that X squared is 0. Yeah, so not X squared equals 0, but actually 0, 0, 0. Right? That's what I should.
This method gives some hints as far as how the post set of orbit closures?
No, but there are now computer algorithms, actually, I should point out.
So there's no
for listing
from just classification of orbits?
No, because as I said, an orbit can intersect with many components, so things can go funny. Then he gave the second classification, which is kind of sophisticated. Maybe I go in this direction. Second classification. Sophisticated. Those orbits correspond to some graded subalgebras, which are reductive with certain properties. But this then it's really combinatorial, so you can actually work it out. And actually, I should point out that for incidence of orbits and for orbit lists, there are algorithms by Willem de Graaf.
Sorry.
There's a computer program online.
What you wrote, because I was slow in taking notes, and now I don't understand.
So second classification is
take a nilpotent orbit. No, just what you wrote.
Take a nilpotent orbit in G, in big Lie algebra, intersect with G1, and then take irreducible components. In this way, you will get all the orbits. And that's a simple tangent space argument, okay? Anyway, all right.
But I guess with Luke's question, though, is that this is a finite list. People probably know everything about these, don't they?
As of last year.
Which finite list? BN, CN, DN? This is not a finite, but that's right. Let me tell you, because I want to focus on actually E6, E7, E8, because for classical things, you get kind of things similar to determinantal varieties. So, you have some other rank conditions. So they are kind of, you can describe by linear algebra, but those E6, E7, E8 are are kind of exotic, like this wedge 3C6, wedge 3C7, wedge 3C8. All right. So here's, and what basically happens, it's kind of disappointing from the point of view of orbit closures. So basically, let me just say that every orbit closure.
Sorry to keep slowing you down, but I got what. Can you say just a few more words about this second classification?
God, no.
Okay.
Because it would take the series of lectures. Yeah. No, it's sophisticated, I mean, but well, one can do it even by hand with very few mistakes, let's put it this way, if you like work on it for one summer or 2 summers, you know, but Willem de Graaf is the algorithm that gives you even the incidence between the orbits, okay? So this is like all. Anyway, and there are many orbits, by the way. For E8, you can get like 62 orbits, for example, in the worst case. So there is some work to do.
62.
60.
That's all?
That's not bad. Okay, right. Unless you want to calculate all 3 resolutions, right? But yeah, that's maybe too ambitious. But anyway, so every orbit closure is a subspace variety. Let me say, has the singularization by a vector bundle. Okay, so I have probably 15 minutes, so maybe I will just give you one example. Let's take the XR inside of X, which is Hom CM just the example of determinantal varieties, matrices of rank smaller or equals than R. Then what you can do, you can desingularize it. You can find variety Z, which will be inside of X times, you can take Grassmannian of subspaces of dimension R in Cn.
So these are vector bundle where? So you are on G1?
Vector bundle on some G mod P.
I see.
It's for the smaller group already. So basically, yeah, the usual, you know, the Kemp non-stability. Every orbit closure is a stratum, you could say. Or okay, that's maybe.
But you are taking the affine orbit closure or the projective?
Affine. Everything is affine.
Everything is affine. Okay.
So, for example, in this, for determinantal varieties, you have this classical thing. You can take the pairs of maps phi and the subspace R inside of the Cn such that image of phi is contained in R. All right? And this, you know, since the dimension of R is R, clearly you project, the image will be XR. And it's very easy to show that's a desingularization and so on. And
so every orbit closure
for those special representations of this Windberg theta type, the Windberg type 1, every orbit closure is this subspace variety. So then you have this kind of mumbo jumbo, this cohomological thing, and basically what you can do this Borel-Weil bot technique.
Weil.
That's right, it's an unexpected, Weil. Right? Yeah. Sorry. And basically what you can do, you can give the upper bound on free resolution. I will be vague here. And you can give the lower bound.
You mean the length?
On free resolution. No, on modules even. Basically, you see, it comes down to calculating cohomology groups of G mod P on the versus our G mod P over which this desingularization lives on some XCO powers of some homogeneous vector bundles, okay? So you can take a lower bound by taking Euler characteristic, and you can take the upper bound by changing this to associated graded, because it becomes technical if psi is complicated. So you have something in between. All right. But what does it give? Well, for rational singularities, you need a lot of vanishing. But in fact, one can get it So what happens, and this is, by the way, the work of Kraszkiewicz, I guess, and myself, that in those cases you always can claim that every OX, at least the normalization of OX, has rational singularities. Okay, so higher direct images vanish, although the coordinate ring might be not normal, and it is quite often.
So this is for every.
For every of those Winberg theta. Yeah, that's right. Like the same thing happens for nilpotent orbits, for example, closure. So it's not really unexpected. So it's, you expect singularities to be mild. Yeah. All right? And for normalization. Yeah, so you see, the orbit closure is not normal, but somehow if you take a little bigger ring normalization, it behaves nice.
I thought there is only one normalization. So.
Yeah. For each orbit closure, you have normalization. Yeah, that's right. Yeah. Okay. And now you see, it turns out, but you are still, if you want defining equations, this is not enough even for normal orbits, because those bundles psi are complicated, and your calculation of exact homology group is really beyond reach. But you can use the following trick, which was done by Federico Galetto. Let's say for normal orbit closures. But for non-normal, also one can, it gets a little bit complicated. So what you do, okay, use, I'm talking now E6, E7, E8. Okay, so you can use computers and you can try to use Macaulay 2, the wonderful algebra system. But of course, to calculate any of those resolutions, that's way too big, okay? Way too big. So what you can do, and actually he succeeded in maybe 1/2 of the cases, let's say, is the following. From the lower bound, you can get the expected complex,
In all those cases.
That's right. Can get the expected complex. But of course, you don't know. You get G modules and expected maps, but you don't know whether there are no ghosts in the resolutions. There could be the same irreducible occurring in neighboring places. It occurs in the resolution, but it cancels out. But in those cases, what happened was, so again, Macaulay 2 was too busy, but too difficult. But you can do the following interactive proof, which I thought was interesting. So first of all, you identify an easy matrix some matrix of low degrees that you can actually write down in this expected complex, somewhere in the middle sometimes. The easiest that you can, okay? So you can write down and then start calculating, so it will be some fi to fi minus 1, some matrix X, and then start calculating syzygies of X and X transpose. But only calculating first syzygy up to the expected degree where you expect the complex to go. Okay? Then the calculation is small. And actually, in the cases, well, he succeeded for, E6, F4, G2, and some cases of E7. So in this way, you can get matrices.
You have to do that for every I.
That's right. You have to go first syzygy going this way to the end and that way to the end, to the transpose. It's Cohen Macaulay, so it doesn't matter. Anyway, you can get matrices of expected resolution.
Don't some of these have pretty big codimension?
Oh yeah. You will see example hopefully in a second if I have time. Yeah, I probably will have time. Anyway, you get matrix of expected resolution, and then what you do, fortunately we have this finitely many orbits, we can use finally these properties. There's a kind of classic theorem of Buxbaum-Eisenbach, the exactness criterion of the free resolution. Okay, so let me just formulate it because it's useful. Exactness criterion of Buxbaum-Eisenbach. So suppose you have like S to be actually n Noetherian ring, and you have a free complex. So you to 0, Fn, Fn minus 1, F1, F0, D1, Dn. So you think of this complex as being the set of matrices over this ring with some fixed formats. And then it just tells you when this is acyclic. So F is acyclic if and only if two things happen. First, well, think about vector spaces. So when a complex of vector spaces would be acyclic, finite dimensional vector spaces, of course you would have to, it's a complex, so if you take a vector space, the rank of this map plus rank of this map has to be equal to the rank of the vector space in the middle. Then you will have exactly that it's exact. So a rank of di plus rank of di plus 1 is equal to rank of fi for every I. So that's kind of the obvious thing. And then, well, there has to be something with the ring, right? So you have to use some ideals. So if you have this rank di has rank ri, so you look at the ideal I of di, which are ri by ri minors of this di. So you need to know that codimension of this I of di is bigger or equal than I for every I. So those ideals have to have, this. The place where the rank drops here has to be codimension bigger or equal than 1, bigger or equal than 2, bigger or equal than 3, etc. Okay. So you see now what
I don't understand. Can you say what I of di is again? So di is a map.
You know the rank of this map, it's Ri. So you have the matrix of rank Ri. You take all Ri cross Ri minors of that matrix.
Okay.
Yeah. And that, so all those ideas of minors, the codimension has to go up. So if you ever have an explicitly given complex, that's the way to test, okay, that it's acyclic. So you see now what Galeto does, he had all those horrible matrices, which you don't even see because the entries are complicated, so you just store them in the memory. But now, they're equivariant by definition. So now you have also the representatives of the orbits, okay? So you just evaluate them on the representative of the orbits. You know codimension of the orbits, and you apply Buxbaum-Eisenbach, so you can prove that all those complexes, expected complexes, are really cyclic. And that basically does the job, okay? So this is done for...
So do you require Cohen-Mac coordinates here for the...
Well, yes, you require, yes, but if the orbit is normal, as I said, it's Cohen-Macaulay, so you can go both ways. Actually, all those minors, all those places where it drops rank are the same. And you, yeah. It doesn't, yeah. This is for general complex, but in our special situation, since the thing is Cohen-Macaulay, it means the dual complex also is acyclic. Anyway, so this he did for E6, F4, for G2, and some cases for E7. So actually, the case for E7 is the most beautiful that he did. Oops, okay. It's so here's this. Here's the picture of which 3C7 with the group GL7 acting. So your 3 tensors in 7 variables, right? Skew symmetric tensor in 7 variables. So there are not too many orbits. That's why I picked this. There are just 9 orbits. So I wrote their dimensions, their representatives. So what happens actually is that actually only maybe the most interesting are those 2 orbits. Maybe this one and that one, because you see those orbits here, you can see that orbits below, well, let's maybe go, I still have some time, you can see these are just tensors of rank 1, these are, tensors of rank 2, but they are divisible by a linear tensor. These are general tensors that is divisible by the linear tensor. So you can give kind of the interpretation to all of those, right? This is the second secant of the highest weight vector. This is the third secant of the orbit of highest weight vector. This is a hypersurface because there's only one kind of small interesting fact is that there's one invariant of degree 7 here, delta invariant, SL invariant of degree 7. And the good way to see it is to actually, you can see its cube. If you take a linear map, the obvious linear map from a wedge 5C7 tensor to wedge 2C7, this will be 21 by 21 matrix of linear form. This gives you non-zero invariant. This gives you the determinant is delta cube, or whatever this worth. Yes?
I'm pretty lost, but I can understand.
Yeah, sure. Yeah, so these are representatives, these are orbits.
We have lambda 3C7 with GL7 acting.
That's right.
What you have thrown, there are
That's right. So the basis is 1, 2, 3 up to 7. And 1, 2, 3.
all possible orbits.
That's right, E1, E2, E3.
Those are representatives.
These are representatives of all possible orbits. So this is a general orbit. This is an open orbit. Okay.
So this means degeneration, so inclusion.
This gives you degenerations. That's right. Sorry, I was too quick. Yeah, in a hurry. And then, so this is. I also wrote the dimension of each orbit.
Which of these orbits are closed?
No, closure of the orbit is union of those. That's right. Only the bottom one is. That's right. Yes.
Any of those to the Grassmannian? Just to
Yes, that's right. This one is a cone over the Grassmannian. Cone over.
I understand. But so the other ones, are there some higher, like related to secant rise?
This is the first secant. This is the first secant, sigma 2 of Grassmannian. This is, I believe, sigma 3 of Grassmannian. So, you could talk about rank of the skew-symmetric tensor, right, in the same way, and how many decomposables you can, write it.
What do the numbers mean? So this
Dimensions of the orbit closures.
the right-hand side in the parentheses.
On the right-hand side, on the parenthesis.
EI wedge, EJ wedge, EK is.
Yeah, this is 1, 2, 3 is E1 wedge, E2 wedge, E3. That's just what tensor it is, representative of the orbit.
Okay, I understand.
Correct.
Okay, yeah.
Okay, and
So that's how you see that the third secant, that's the biggest orbit with 3.
okay, so
Well, yeah, I know, it's,
I don't understand.
you are lucky. I could have written the list with 62 orbits, you see, then what would happen? Yeah. But anyway, so that's what it is. And, so these two have quite nice resolutions. Let me just give you maybe one of them, and that's what this Galetto confirmed, with writing down matrices and everything.
Do you have a geometric interpretation of 06?
Let's see. This is a singular locus, right? 07 is a singular locus of that one. This 06, I don't remember. I have, I think, but I don't remember right now. I don't remember by heart. Yeah, but that's an interesting. Oops, sorry.
Because you actually, your paper with Andre, you studied the singular
Yes.
set of the dual variety, and
No, I have interpretation of equations of the 06. Okay, so so here's the equations of the 06, for which 3C6 you have the determinant of degree 4. So if you take all polarizations of you have invariant of degree 4. If you take all polarizations, this gives you reduced equations of this 06. But let me just do 07 since I'm out of time. Let me show you. You get quite nice, for those orbits of low codimension, you get quite nice resolutions, and there are still some of them that we would like to do, especially for this E8. So you see, you basically get this, I don't know. So 07,
secant.
so you get length 4.
It's a singular locus of the third secant.
That's right. So it's a singular locus
okay, so
of hypersurface, right? Delta equals 0. So you get the following thing. I will write Schur functors now as 6, 5 to the 6, E. E is my C7, tensor A, tensor S, minus 12. Maybe let me do it like this. 5 squared 4 to the 5th e tensor s minus 10, s 4 3 to the 5th 2, the adjoint representation tensor s minus 7, s 3 to the 4 2 cubed e tensor s minus 6, and here you have s. In this case also I should say that Luke Edding has some work on, he could basically, I think for the equations, he could, I think, at least write down, guess the right equations and write down that they actually vanish on the orbit closure. So you see here what you have, actually the matrix you start with, to do this Galeto thing, you start with this matrix because it's linear. So you see, this is adjoint representation. This is really up to determinant some third or fourth XTO power. So such a linear map can be written down. Okay, it's not too big. So then you do this, going up and down. And of course, what you see here, again, it's wedge 3 in degree 6. These are just partial derivatives of the invariant. Okay, but not so easy to write down. That the entries are horrible, and then by doing this, going both ways with syzygies, you get such nice resolution. Okay, so that's more or less everything. E8 is still too big, definitely too big to handle even with computers. Okay, and it's a pity because especially in this spinor representation, like E8, when you put the first node, there are one expects some really beautiful Gorenstein resolutions, which are even pure. There's one irreducible. They're really magnificent. 3 of them, codimension 4, 10, and 14. So I would really like somehow to see once, that one can write them down.
Questions?
Yes.
From this resolution, or for any of the examples, can you read off the desingularization that would work to use the...
There's a kind of uniform way of reading of the desingularization for each orbit closure.
After you use the guess for the resolution, can you then go back and say, okay, here's the vector bundle? And
no, first of all, the choice of vector bundle is not unique. Sometimes you have like many. You could have 5 or 6 of them. It's just completely somehow, The data is kind of, I would love to analyze, how they vary from one to another, but they're just too much data. You get those horrible files, and which you have like, 100 of complexes, whatever, So, but definitely, for some orbit closures, there's a unique desingularization. For some, there are more than one, and they are not obviously related by any symmetry that one can kind of see right away, okay?
So they're always have a desingularization of the form.
That's right, exactly. Yeah, it's just by SL2 triple. You do SL2 triple, and it really goes back to Kraft-Procesi, and you take bigger or equal than 2 degree. Yeah. Mm.
So I was wondering whether you have understanding of which V lambdas occur on the orbit closure.
Oh yeah, I should point out, even though the orbits are easy, representations are easy to work out. The symmetric algebra with 3C7. You get horrible multiplicities because the only thing that happens is there's just one invariant, so there are no SL invariants, but the other weights you can... Oh yeah, well, also, there are formulas, the same cohomological formulas, if there's vanishing, Euler characteristic will give you the composition of S mod I, okay, of, components, graded components of S mod I. But, okay, so you get, in a given degree you can calculate, but somehow I don't know if there's any meaning.
Vanishing, does it occur or not? Do you get any better algorithms?
I don't know. Hard to say at this moment.
Any questions?
Yes.
So you gave a big picture, but are there some small examples that are still open for that you could calculate, say, equations or for syzygies that you don't know, but would be sort of small enough for somebody to do?
Well, I think one of the interesting cases, is C3 tensor wedge 2C5, if I remember correctly, which seems manageable. There are not so many orbits. And there's actually one very interesting, when the orbit is not normal, then you can play what I call the co-kernel game, okay? You get the module, which is normalization module of the ring, and then the thing supported on smaller orbit, and then you try to see it as kind of a twisted version of this, and see whether you can do. So there's one very interesting orbit there orbit closure which is not normal, and we cannot figure out how to play the co-kernel game. That actually would be like the first example to look at. And this is E7, so it's not too big. You know, it's not just this co-kernel is not just directly one module supported on the smaller orbit. And I think like this analysis would give, you know, some kind of deeper understanding as to what happens in general. So this example, I think, is significant somehow for more general, you know. Yeah, I can show, I think, the orbit. Maybe not today, but I can send you by mail. Yeah.
So the question, did you classify all the conventional resolutions?
Yeah, so in particular, with Kraszkiewicz, actually, the Hilbert series of normalization, we calculated for up E6, E7, E8. And then clearly from Stanley theorem, you can see the symmetry property of the Hilbert function gives you Gorenstein right away. Yeah.
Do you have many examples? Or
Yes, especially in this, in some, it depends, it varies in a wild way. For E8, for example, in some, if you take C4 tensor weights to C5, which is kind of the biggest, the one with 62 orbits, you get very few normal orbits. It's kind of disappointing. But in this spinor, V omega 7 D7, right? I mean, then in this you have, I think, maybe even every orbit is Gorenstein or something like that. Most of them are Gorenstein, and there are the really beautiful, you know, expected resolution is so nice that it just must mean something. So it's, yeah, so that's somehow.
So there is no more question. I have none.